Electric potential energy is energy that arises from the interaction between two objects that have electric charge. We can consider it to arise from the electric charge of one object interacting with the electric potential of the other object. This interpretation is consistent with the units of electric potential, which you recall are joules per coulomb. This is the equation for the electric potential energy of a point particle. It depends on the net electric charge of the point particle and the electric potential experienced by the point particle. This is not the electric potential of the point particle itself, but rather the electric potential of the other objects in the system that interact with the point particle. The electric potential energy of two point particles, A and B, can be considered to arise from the interaction of the net electric charge of particle A with the electric potential of particle B. Alternatively, we could consider this electric potential energy to arise from the interaction of the net electric charge of particle B with the electric potential of particle A. Either interpretation gives the same final expression, as expected from Newton's third law. The electric potential energy of a system of point particles is equal to the sum of the electric potential energies of each possible pair of point particles in the system. Now let's calculate the electric potential energy of this system, which consists of a uniformly charged rigid rod aligned with the longitudinal axis of a uniformly charged disk. We can consider this electric potential energy to arise from interactions of tiny bits of electric charge in one object with the electric potential of the other object. If these bits of electric charge are infinitesimally small, we can model them as point particles and use the equation for the electric potential of a point particle. Although we could model either object as a collection of point particles, it is easiest if we model the rod. The reason for this is that we already have an equation for the electric potential of the disk along the longitudinal axis, and thus we have an equation for the electric potential of the disk at any point along the rod. We do not have a similar equation for the electric potential of the rod at every point in the disk. Thus, the variable dq in the equation will be an infinitesimal bit of electric charge in the rod, and the variable v sub e will be the electric potential of the disk at any point along the rod. As we've done before, we can replace the variable dq with the product of the linear electric charge density, denoted by lambda, and the variable dz, which denotes an infinitesimal bit of length along the rod. After a bit of simplification, we determine an expression for the infinitesimal bit of electric potential energy associated with the interaction of an infinitesimal bit of electric charge in the rod and the electric potential of the disk. The total electric potential of this system is the integration of all possible interactions between point particles in the rod and the electric potential of the disk. The limits of this integration are from d to d plus L. These limits denote the closest and farthest any constituent point particle in the rod can be to the disk. After performing the integration, we arrive at our final expression after a little bit of algebraic simplification.